I go by my second name. My first name is Jesse, but I go by the second name, which is Dee, D-E-E. MC, my last name is McCullough, M-C-C-U-L-L-O-U-G-H.
What was your job here?
As started out as a instrument technician, became a supervisor, instrument supervisor, then ended up as senior engineer. I don't recall I had several engineering jobs. Each time I worked for a good number of years and retired and was brought back to follow a job for a remodeling job. So they elevated my position, and then I retired once again and came back again to cover the write-up of the project for renewing Reactor for another 25 years, which was then reduced to 10 years and then canceled together. So at the time they canceled it, then I retired from the last time.
Well, can you go back to what you were telling me as we were walking over here about how you first heard about Hanford, what you were doing, and how you happened, to come to Hanford?
Okay, I was working at the Utah Ordnance Plant as an instrument technician. And then I inherited the patrol radio system, that I maintained that. Worked for a fellow that had charge of the telephone office, telephone exchange. Then when they indicated that the plant was going to be closed down due to the fact that other factories were making more machine gun shells than what could be fired, they, even though the war was still going, they closed the plant down and said that I would be transferred. I could either be transferred to Hanford, and I said, I'd rather stay here and follow the shutdown of the telephone system. I said, oh no, we'll get older men to do that. You either go to Hanford or go to the Army. So I went to Hanford.
And what did you find when you got to Hanford?
So I arrived at Hanford on the January 3rd of 1944, and was taken by bus, met by bus at Pasco Depot, brought out to Hanford, and there went to long lines of sign-up, and the fellow that was escorting me bypassed all the construction workers so I wouldn't have to stand in the long lines. And I was signed up, assigned to a barracks in Hanford. And I spent about 3 weeks in the barracks there. And one of the experiences I had there was a fellow I came with said one night, let's go to the movie. They'd had a movie in a tent up until that time, and they had just started up a permanent movie house out there. So we went over there for the opening night, stood in long lines waiting at the ticket booth when the usher came by and asked me, told us that there would be a delay because they were having trouble with sound systems. Well, the fellow I was with said, well, you're a sound engineer, why don't you tell him? I'd been a sound engineer before I went to Utah Ordnance Plant. And so I said, I won't bother. Well, the next time the usher came by, he told her, and so they brought me into the booth and into the theater, took me to the door to the theater, to the opera, to the picture booth, and yelled up that they had a sound engineer down there, and, well, we don't need any, we've got one from Seattle. So they said, well, go in and sit down, buy your tickets, go in and sit down, it's no use you're going outside. Well, a few minutes later, here walked down the man down the other aisle, which I knew. He'd been a competitor of mine at the theater supply house I worked at before the war. So I yelled his name, and he turned around and he said, Dee, if anybody I wanted to see, it's you tonight. So my experience at Hanford was to go with him, and we used voice wire phones and rang out the lines, which had been extended, and the color codes of the lines going to the speakers were different than that going out of the booth. So we rang out the lines and had the show going very shortly. So that's my experience with Hanford. Other than the fact that we could have our dinner there in a long eating hall that settled 2,000 people per building. And we could go in and they'd lead us down seat by seat, feed us all we could eat. If we emptied the plate, we'd raised it up, and they'd come and pick another, take that off and restore it. So we could eat all we could eat for 67 cents. So I stayed there for about 3 weeks and moved in the first dormitory in Richland.
So that was what Hanford Camp
Okay,
was
hang on a second.
Hanford Camp. Mm-hmm.
over again, so that they can get it on film, right?
Yep,
Start where?
you were gone.
Okay, why don't you tell us about that?
I was told to buy 2 books. The second one was on for laboratory experiments in universities, covering measurements of alpha particles and gamma rays and that sort. So I knew that I'd be working with something involved with gamma and alpha particles and that sort. And my first work was in the 300 area, and they had a little test reactor. When I first had my first lunch in the 300 area, I was brought in from Hanford for I might say sightseeing tour, but they introduced me to the engineering department, and they made all drawings available to me regarding instrumentation, especially in the little test reactor. So I went to lunch with a fellow that had come up from Utah Ordnance Plant earlier, and he said, well, I don't know why you can't go into that building. He said, all they have is a big U-shaped piece of concrete that people came out from Chicago telling us how close we had to make holes through the back face of that concrete. Well, it turned out to be the 3 walls of the little test reactor in 300 area. They filled that reactor area with graphite, with holes through, just like we do in the present reactors. And we would fill those holes with uranium slugs, and we would measure them with test instruments that we had. In fact, I maybe got ahead of myself. At the before we started to load, I was assigned to follow the installation of the 3 nuclear safety monitors in this little test reactor. They were the circuit diagrams for those amplifiers is completely different than what I was experiencing in the theater equipment. But anyway, we installed the three and with chambers underneath the reactor, with the ion chambers that fed these meters. These meters were microammeters, or call them picoammeters, but they were to measure 1/1,000,000 of an ampere. And we had a problem with them that if we moved the signal cable to it, the meters would go full scale and back. They were so sensitive that any static charges, anything would cause problems. Well, I was going to say my later experience, I'll go to that after. But we loaded this reactor, partially, and then take measurements. And the physicist that was there, which I don't remember his name, said, we need more fuel. So they loaded more fuel in. And finally we got to the point where he said there was sufficient, we had sufficient. And he said, well, what power are we getting? He said, about 1,000 watts. And let it go at that. Well, let me close down and let the construction come back in and put cement blocks on the front face and had it enclosed. The reactor was built with a scaffold that would feed a channel of either graphite or fuel elements into the reactor. So we would set the measurements so it would be reading normal. Then we'd insert a channel of either fuel or graphite and watch the effect of it. And that determined whether the fuel was pure or what the purity of the fuel or the graphite which we were testing. So the primary purpose of that reactor was just to determine the purity of what went out to the big reactors at the plant. But the problems we had was static problems. I was given 10 of these instruments, microammeters, on the wall in the instrument shop. And my job was to try to determine what was causing the static installation problems that we had. I tried.
Was this at the test reactor or at B reactor?
At the test reactor.
At the test reactor, and
that was a few months after I was there, and in fact about the second month. And then I finally made several changes, and the supervisor come in and he I could flip a fluorescent light on and off, and these meters would fluctuate. And he said, what have you done to this one? I said, nothing. He said, it's more stable than the others. So then we finally did more testing, and finally, when we decided what it was a little wire-wound resistor that was only 2 ohms in resistance, wrapped around either, I guess, a metal spool, along with some other resistors in it. So by putting a very large capacity across that little resistor, I was able to settle it down considerably. So we decided what we would do was rewind that resistor. Instead of winding it all the way around one way, we'd wind it halfway around and turn it back, run it around, to make it non-inductive. And then when we got to this one that was from the stable one, we found that the wire had been wound, or the resistor had been wound by a wire considerably smaller in diameter than the others. So it took far less turns. So then it verified the fact that we found it. So then we had the Beckman Company in Los Angeles make those changes in the amplifiers for the ones that went out to the plant.
So when did you get involved with the B reactor?
Well, then they sent me to the Beckman factory for 3 weeks in April of '44. And after that, then I was sent out to the B reactor. So that would be in the early May of '44. And there I followed the installation of these Beckman instruments. And we not only used them in the nuclear safety system, but they were also used as area monitors around the building and also around the area. And but the chambers that supplied the current was located underneath the reactor. The reactor stands on about 10 feet of concrete, or 12 feet of concrete. 20 feet of concrete. And there was channels going underneath through that concrete. And then from those channels, there's chimneys going up to the bottom of the reactor. And we'd place these chambers underneath these chimneys. And then we checked the response, or we put a strong radium source in the reactor. That was before any fuel was loaded. And determined the sensitivity of it. We decided the chambers were too sensitive. So we pulled them out about halfway, so they were only halfway exposed. And decided that would be sufficient to take care of the installation. So then they started loading fuel. When they loaded fuel to the point where they started to turn, they loaded fuel so far till we had activity with no water going to the reactor. And then after we got to that point where we thought that what we call dry critical, that's what the scientists, Enrico, Fermi and such, figured was dry critical. Then they started water flow to the reactor and loaded the reactor the rest of the way with fuel. And I might say that the early design was to only have about 1,300, I think, fuel elements and or fuel channels. And they loaded them up and started the reactor. Then we got involved with this xenon poisoning, which the reactor level was starting to go down. Meters began to go down off scale. So Enrico Fermi asked me if I could, he says, I can only bypass one of these 4 channels at a time. Do you know which channel belongs to this meter? Yes. Well, you go down there and remove that one, restore that one to the original position. Okay. So I went back. Yes, that was all right. Now I'll bypass number 2. Well, we were still having trouble with signal cables, moving them. So I had to make sure that I didn't touch any cable that went underneath the reactor, except the one that I was supposed to. But anyway, we did that for all 4 instruments that was there. So that was my experience with Enrico Fermi.
So you told me he came out for...
We're about 19
Yeah.
minutes right now.
Yeah, he was following the instruments at the time that this was taking place. Now, we also used similar chambers for the galvanometer systems that read the small lights that went back and forth across the screen for the operator to use to determine power level. So those chambers, and we had similar problems with them that we had to work with. So that was my involvement.
Yeah.
How involved was Enrico Fermi, and what kind of a person was he?
Well, I never had too much experience with him except just talking with him at that. But he was very, as far as I could say, personable. Now, when he came out here, he was called Dr. Farmer. And I had to have somebody from that came from Oak Ridge say, oh, we knew him as Enrico Fermi back there. But out here, it was Dr. Farmer.
Tell me about Leona Woods and what you remember about, when it,
Oh,
the
yeah.
mysterious,
There's John Marshall and his wife brought me on the name.
Leona Woods. Marshall.
Leona Birch, or Marshall. She had a 20-inch slide rule that she did all of her calculating for these other engineers, John Marshall and John Wheeler and somebody else, I think. There. Oh, Enrico Fermi. Those three engineers or physicists were there, and she was supplying all of the calculations for them that I can remember. But she sat in the room right back of it. But I can remember her working. I was familiar with a 10-inch slide rule, but I never had seen a 20-inch one before.
And she came out with them when the
Yes.
reactor first went critical.
Mm-hmm. And I have a booklet, early Hanford history, I think, that she has an article in there where she said that she and the other physicists were standing on the back wall, I guess in front of the panelist system, watching as they started up. And when they were dying down, and they were all laughing and making comments about, well, they were trying to determine how long it would be before they could determine what was wrong and when they could get it started. And these physicists were making bets with one another who would be able to find the problem and start the thing up again.
How long did it take to find the problem?
Well, that shift I went off, and the next morning I talked to another instrument shift supervisor that lived neighbor to me. He said they'd started up. So it was over the night and they'd started up.
But had they analyzed the xenon poisoning right away?
Yeah, they knew. Oh, and what they finally had to do was determine that they had to have more power, or more fuel elements. So then they went and loaded the full 2003 channels with fuel. But the early engineers, early studies, they only needed, I think it was 1,300. But the local designers decided, well, we'll just go that much more to take care of any possibilities. So it was a good thing they
Does the name
did.
George Graves mean anything?
Who?
George Grave?
I think so. I can't remember all of their names. But
Stop tape for a sec. Great, why don't you tell us about the safety?
well, the early design of all of the reactors here they were very serious about safety. And well, now our control rods were hydraulically operated by oil hydraulic pressure. As you come into the control room, the room right before that, you'll see 3 big tanks that were filled with heavy rock. And before the reactor would start, they would pressure them up, raise them up high. So if we lost power to our hydraulic pumps, these big tanks would supply the hydraulic pressure to operate the rods. So that was one of the main safeties. The panlet gauge behind us is another one that monitored the flow through each process tube, not only the total flow, which we also had monitoring for total flow. That would, loss of flow would shut it down, but loss of any flow through any one process tube would shut the reactor down. Therefore, we had 2,003 of these tubes, all with little mercury switches in them, that if one of them would open circuit, the reactor would go down. So we had to be very careful to maintain that very well. And above the reactor, there was control or safety rods, 29 of them hanging up above, and they would fall by gravity into the reactor. And if we needed more safety, then they could release the catches on those and drop those 29 rods into the reactor to shut the reactor down. And then, again, safety after safety. They said, well, in case of an earthquake, that would cause those channels to be disrupted, so these rods wouldn't fall in. So they provided a boron liquid solution in tanks above the reactor. So if they would, if the rods wouldn't work, they could dump that solution into the reactor. Well, we never had to use that, thank goodness. But before long, they replaced that solution with boron balls, small, about 3/8 inch diameter balls that were boron that were up there so they could drop down. And we've had to use them a couple of times. And they could be vacuumed out. But
Well, that was the reason for the balls, right? Is the extraction? Could you talk about that? What the reason?
it's just say it would be the third safety. The control rods here, the vertical safeties, and the boron balls. And of course, we protected ourselves by loss of water. If a fuel element should expand and cause water flow to stop going through a tube, then we'd get a low flow trip on the panlet gauge. If a fuel channel should break and allow water to go into the reactor, cause a high flow, then a high flow trip on the panlet gauge would shut us down. So they had.
Looking back over your experience with the B reactor, is there some aspect of it that you think we ought to know about, or you think was most memorable, or you feel most proud of, or?
Well, we started out with the maximum power, if I remember correctly, about 150 megawatts. And one day came in and they said, they had an extrusion right up above that. We've got to remove all the charts and put new charts on because we didn't want to show these that high level. And so then, of course, later on, advancements went to the point where I think these reactors were operating, instead of 250, they were operating at 1,000 watts or more. But it was just the fact that we were able to change the amount of flow and other features that would allow us to get more flow, more power.
If there was one technical feature that you think sort of stands above the others that allowed this technology to work, what would you say it is? What would you say was the real aha genius feature of these reactors that allowed them to be?
I'd have a hard time. We had more problems with the panlet gauges, these pressure monitor gauges, back causing scrams than any other system because of the little mercury switches and all. So in the end reactor, we replaced the pressure monitor with an actually flow monitor. These pressure monitors read took the signal off from a line beyond an orifice in the inlet of the process tube. So it was only reading the downstream pressure. They had to keep the pressure from the pumps building constant in order to make them work. Well, with the end reactor flow monitors, it was a complete differential pressure type device where we didn't have that problem. So I had to do with the development of the flow monitor for the end reactor.
We're gonna have to change tape.